Hopefully it's not too noisy. It feels like a noisy morning out there. I think people are starting to get the sense of maybe someday, not too far down the road, things going back to a little normal and people are out and about and doing things, which is awesome. Hopefully. But anyway, I'll close Windows if it gets too noisy out there. But let's go ahead and get started. So yes, good morning to everybody. Hope things are good. So any questions? PA2 in particular, we're going to talk about building up structures today. So we're going to be discussing things outside of PA2, heading more towards PA3. So let's talk about questions on your indexer class up front, if there's any remaining questions. I had 11 Git repositories uploaded and sharing with me as of this morning out of 40, so hopefully people are working and just not pushing over to Git. Although better if people are working and pushing over to Git. Alright, well, let's go ahead. I have a question about the midterm. Like, when is it happening? When is it and is it happening? That's a really good question. I'd like to know the answer to that because I have to write the thing. Midterm, May 15th. Wow, that's 10 days away. That's not too bad. So PA3 will be announced on Friday and will be due on the 20th. So the midterm will be in between, while you're working on PA3. And the midterm will be pretty much everything we've done up to that point. So definitely, concepts of objects and classes and object-oriented programming, writing a class, writing a main method, using some of the built-in classes like string, linked list, hash map, okay, all the PA2 stuff, creating classes on your own, working with them, accessors and mutators, setters and getters, all that sort of stuff. So if you've been working on the assignments and they've been making sense and you've been doing this stuff right, it'll probably be just kind of more of the same. Nothing new or startling there. All right. Well, so we know that there's built-in classes like linked list, right, which give us a linked list, and they're very powerful. They're presumably very efficient, and they're generic. They work with any kind of object that we want. A linked list of integers, strings, rectangles, whatever, and that's great. We mostly in Java will use pre-existing classes when you do things like Android development. You don't really write a whole lot of low-level classes. If you want to know where you are, you just construct an object of a certain type from a GPS-related class, and you call a method. And when your position changes, your method gets called, and it tells you what your new position is. I mean, it's mostly grab stuff and put it together. But for this course, we still want to learn more about putting together classes ourselves. How to create these things from the ground up. And a good framework in which to do that is with some of the data structures we worked with in 222. So I want to look at linked lists, okay? And this is if you wanted to build your own linked list, right? How would you go about doing that? And so let's envision a class, and I'll just call it MyList. And it's going to create a list of nodes, okay? Nodes are going to be things that have a piece of data and a reference to the next node, so two fields inside a node. We're going to create our own nodes, okay? So this is kind of like, the outer wrapper on our list. The nodes are kind of like the struct nodes we did in 222. So a class, I'll just call it a node. And let's just store a data value that's a string. And let's store a node, which is the next. All right, so sort of what you'd expect. There's no asterisks or pointers or anything like that, right? The next field is a node, right? And a node is a thing consisting of a piece of data, which is a string, and a next, which is another node. So for a MyList, we need a handle to our structure, right? Anytime you create a structure, you got to have a way to get a hold of it. So that when somebody runs this, right, they're going to say something like, you know, so this is in your main method perhaps. You're going to say something like MyList, you know, listy equals new MyList. Okay, I guess I'm doing camel case. And so this thing listy is going to be, you know, a reference to the list. It's really going to be a reference to this object of type MyList. So there's got to be something in here which keeps track of the list itself, right? The nodes. And the easiest handle to use is just the first node. Now, mostly in 222 when we did lists, we made sentinel nodes. I'm going to do this without a sentinel. No particular reason, nothing wrong with sentinels. I just want to go a little deeper into the code. So I'm going to make a field here, and I'm going to make it private. And I'm going to call it first node. And this is going to be an object of type node. And I'm going to initialize it to null. Okay, first node is the first node of the list if there are any nodes. If there are no nodes, first node is null. So it's not a sentinel, it's actually the first, you know, node containing data, or it's null if we don't have such a node. Which you won't when you first construct a list. So that's the essence of our linked list. It's just that one field called first node. And then mostly let's just add things. So let's make a void method called add, which takes a word. And so the idea is in our main, after we create this linked list called listy, we can say listy.add. And we can put a string in there and add something to the linked list. And let's do this alphabetically. So increasing lexicographic order. And so we want some code in here to insert. So, you know, here's our linked list. Here's first node. We're going to create a new node, right, containing this word. And we'll call that temp. So we make this new node. And we're just going to move down the list, right? Actually, I'm going to call this new node. I'll use temp for something else. So we make a new node and we move down the list. And at each point in the list, we say, should the new node be inserted right after this node? Okay, and if it should, then we have new node point to where this node's pointing, and we have this node point to new node. So the same drill from CSE 222 in winter. And there's edge cases to worry about because we can run out of nodes, because we might want to insert before the first node, because we might have no nodes in the list at all. Okay, so we'll deal with those edge cases that we got to ignore when we had sentinel nodes. But basically, how do we know if this node should go before that one? Well, if the word in here is less than the word in here, then it belongs before that. Okay, so we'll use the compare_to method in the string class, which returns 0, positive, or negative. And so if this compare_to that is less than 0, then this comes before that. So let's just put this together in code. So let me make my node class. This is a simple node for our linked list. So it's going to be a linked list of words. And this is a pointer. Not really. Yes, really. To the next node. Okay? It's not really a pointer because we don't talk about pointers in Java, but it really is a pointer. It's a reference, okay? It's not actually you know, the node itself, because that would be this infinite recursion kind of thing. It's really a reference to another node. Okay, but we don't have to worry about that because it's Java. Let's make a helpful constructor. Because usually when we have a node, we want to give it a value. So let's make a constructor that does two things at once. Creates a new node and lets us store the value of that, of whatever word we want in the data field. So public node string word. Make a new node with this data. And all we got to do is data equals word. And that's it. But, you know, since we're making a node anyway, let's go ahead and set next equal to null. It'll default, but doesn't hurt to be explicit. Okay, so if somebody says, you know, list equals new MyList, paren, that's going to make a list. If we do something like node n equals new node hello, that should create a new node with hello and null, and n will be effectively that node. It's a reference to it. We can think of n as being that block of memory with those values. All right, so our constructor takes a word, saves that in the data field, sets next equal to null. And that's, you know, probably all we need to do in the node class. All right, yay. So Java C node.java, so that compiles fine, no problem there. Okay, we're done with the node class, right? This is this modularization I keep talking about. Make a class, compile it, document it, don't have to think about it again. It's just there, it does what you want, like a string or an integer. Let's see, question. When we were making linked list for PA2, we did the linked list integer. Would it be possible to construct a MyNode class instead of linked list MyNode when using the basic linked list class? Sure, absolutely. So we could make a linked list of MyNodes, right? And it would look a little strange because inside the list, each of the pieces of data would now be one of our nodes that would have you know, a piece of data and a pointer to another one of our nodes. But you could totally do that, absolutely. We could also make a linked list of MyLists, and then we'd have, you know, a Java linked list where each node is a MyList, which could be kind of cool. All right, so let's make the MyList class. So here's public class MyList. So sample linked list class, which will just let us construct, add, and print. Okay, we're not going to worry about anything fancier than that for now. So private node first node equals null. So this is the first node of the list. Or null if the list is empty. All right, we don't really need a constructor because you know, we're already initializing first node to be null right here, and that's really the only thing we need to do to create an empty linked list is just, you know, construct the object, which the new keyword will do, and then set first node to null. So we don't need to define a constructor ourselves. So let's add a node in alphabetical order to the list. So we'll take in a word, we want to create a new node with that word as the data value, and then we want to put it into the list in the correct spot. Okay, and this is not going to return anything. We could return, you know, a Boolean to tell if we're out of memory or something, but that's an exceptional condition, and it would take a bit of work to catch those errors. So we're just going to return nothing. And we will assume that every time you use this method, it works perfectly and nothing needs to be checked. All right, so how do we add? Well, we have to deal with edge cases. Okay. So the first edge case is easy to deal with. That's the case where the list is actually empty. We have no nodes in the list yet. Okay. So what do we do here? Well, let's make our new node first. So this is the node to insert into the list in the proper spot. All right, so we create this new node. Edge case, the list is empty. That's pretty easy to deal with. So if first node equals null, just set first node equal to the new node and return. All right. Well, that's an easy case, right? So what's the next edge case? So we have a first node. The next edge case is we want to insert right before. In other words, the word we're adding should become the new first node. Okay, and it's not because the list is empty, it's because this word occurs alphabetically before first node's word. That's a special case. Okay, so edge case, new node should be inserted right before first node. So if word compared to first node dot data is less than 0, right? So first node dot data is the first node's word. Word is the string that we're trying to add, right? So that thing's compare method. So if the current word's alphabetical position is before the first node's, we want to insert before first node. All right, and how do we do that? Well, change this node. So first node is already pointing to something. Change first node to also point to something. Okay, so that we don't lose a reference to that second node. So new node next equals first node next. And then change first node to refer to that new node. So now first node points to this points to whatever was, oh, I'm wrong. That's not what we want to do. We want to simply have our new node point to first node, and then have first node point to our new node. So new node next equals first node, and first node equals new node, and return. I've been making Minecraft videos, and I'm used to talking pretty freely, and then going back and editing later when I put them together. So sometimes I'm talking before I'm fully thinking it through. All right, so that edge case is pretty straightforward. Just have your new node point to the old first node, move your first node. All right, so we've got two cases. We've got the case where the list is empty. We've got the case where the list is not empty, but you want to insert before the first node. Okay, the more general case is the list is not empty, and we want to insert somewhere after. Okay, so we're going to do a while loop. Let's loop until we find where to insert. Okay, and notice I'm doing my returns here, so I don't need to say else, right? And I don't need to keep nesting these things and worrying about what the condition is here based on that. If this is the condition, I take care of it and I exit. And so here it's as if I'm beginning my code, but I know that my list is not empty. And if I have to go before the first, I take care of it and I exit. And so here It's as if in the beginning of my code, I know that I'm not in one of these edge cases, I can just write a loop. And so I'm at my first indent level inside my, my method. So let's make a temporary. So we'll use this to move down the list. And let me see, we got a question here. In what case would we want to build our own linked list from scratch instead of just letting Java do it for us like in PA2? Like if in a programming assignment it says you have to build your own linked list. Practically speaking, there's not a really good reason to do this, right? The linked list class does everything we want. I can't think of some, peculiarity that we would, not be able to get that class to do for us. But maybe we're not making a linked list. Maybe we're doing something different, right? Maybe we want a linked list that, I can't think of a pathological example. But it's really just an example, because there's going to be other structures that we're going to want to build on our own, and it's going to be exactly the same process as what we're doing here, okay? So I'm doing this just to kind of map 222 building data structures to Java building data structures, so that when we want a structure that's not a simple linked list, it's something we've come up with on our own, we've got that experience of how to implement. But this class that we're building right here, totally redundant, right? It's a watered down version of Java's linked list. Okay, but you could encounter some of this on an exam. So seriously, that's the main reason that you would encounter it in the next few weeks. All right, so we're going to loop until we find where to insert. Where do we want to loop to? So let's look at our linked list. And we're going to use this temp to keep track of nodes. So let's say this is A, B, E, F. And we've got our new node, which is D. And let's say we've got temp, which is pointing here. Okay, what we need to do is compare to temp's next node, right? So look at the node after temp. Should we insert before that? No. So change temp to point here. Should we insert before the node after temp? Yes, right? So as soon as we find a node whose data value is bigger than our data value, we want to insert after our current node. So this is this look ahead business, right? Instead of doing a previous next, previous next, previous next, we're using one node, but we're looking one spot ahead, okay? We can do that because we've taken care of some edge cases. So we want to do this as long as there is a node after temp to look at. So we're going to do the following. While temp next is not equal to null, should we insert before the node after temp? Okay. In other words, should we put our new node directly after the node temp? But I'm phrasing it as inserting before the node after temp. Okay, because when we pop out of this, right, that's going to be our last edge case. So, so while temp next is not null, let's see if that's the node that we want to insert right before. So if word.compare to temp.next.data is less than 0, so if the word we're inserting comes before the next node's word, then the answer is yes, we should insert there. So now we're going to do this thing that I was jumping the gun and doing before. We're going to say temp next equals, sorry, we're going to say new node next equals temp next, and I'll do this in separate lines. So have new node point where temp points, and then let's do temp.next equals new node, and temp points to new node. All right, so we've inserted temp points to the new node points to the thing that was after temp. And again, let's get out of here. right? Because if I don't return, then everything else is going to be in an else statement. And that just keeps getting deeper and deeper in the nesting. Okay, so there's the end of my inserting. Otherwise, so here is where my else is, right? Move down the list. Temp equals temp.next. And then let's just go back. Alright, so we're moving down the list. We're inserting in the correct spot when we get there. If we're not there yet, we're going to keep moving down. Well, this loop will terminate when temp next is equal to null. In other words, when we're inserting h and temp has gotten all the way down to here and temp next is null, what do we want to do in that case? We want to insert after that last node. Okay, so this is our final edge case. So final edge case, insert after the last node in the list. So temp is already pointing to the last node, right? Because we know temp next is null. So just set temp next equal to that new node and return. There's our add method. Okay, so the details aren't super critical here, right? Again, it's the process. It's thinking about how do we do this in C while we're doing kind of exactly the same thing in Java. Okay, it's just the mechanics are very different, right? We're not using arrows and we're not saying malloc and things like that. But the essence of what we're trying to do is fundamentally the same, right? The pictures that we're drawing are the same that we drew a few weeks ago. And the code is doing the same steps. Okay, so let's make a print method so we can look at what's in the linked list. So public void print doesn't take any arguments because what's it going to print? It's going to print the list, right, which is the thing corresponding to first node. So we'll move down the list and we'll print out the data values. Starting with first node. Okay, so what's our while condition? It's pretty straightforward here. There's no edge cases. While temp is not null. So if the list is empty, it will kick out the first time, not print anything. If there's a single node, temp will be the first node. It'll print that, and when we move to the next, it'll be null, and we'll exit our loop. Then we'll just print out temp.data. And we'll move down the list. And that's our whole print method. And so that's the end of our class. And let's see, well, our end of our MyList class, not the end of 223. See how we did. Wow, that's amazing. Okay, so let's make a main program. So we'll make our list. Alright, so there's our words that we're going to add to our list. And then let's go ahead and just call our print method. So just test code, right? And that compiles. Alright, you ready to run it, or are you just going to take my word that it works? We'll go ahead and run it. Hey, that's amazing. That looks like it actually worked. So it inserted those words. Hello, this is a test, goodbye, haha, but it inserted them in alphabetical order, so when we print through the list, it's coming out the way we expected. All right, so 53 lines, right, with lots of vertical space. And yeah, let's look at node.java. So what changes if we wanted a list of integers instead of strings? So this changes, right? We have to say that a node contains a data field that's an integer. The constructor changes. We have to say the thing that we pass is an integer. But the code is the same, right? Take the argument and store that in the data field. Set next equal to null. And what changes in here? Well, this is all the same up top. This is all the same. The add method takes an integer. We construct a new node. If it's null, we do that. That's the same. The compare to is different. We want to say if word is less than first node.data instead of compare to, because integers we just compare with a less than sign, right? If we had rectangles and rectangles had a compare to method, we would say, you know, if word.compare to first node.data, and it would use word the rectangles compare to method, right? So this is more using objects, right? If you give your method a compare to that returns a positive, negative, or 0, then this line doesn't have to change. This line is the same. And all of this is exactly the same, right? Checking for nulls, using the compare to, moving down the list. This line is exactly the same. Inserting at the end doesn't change, and this will come out exactly the same as long as whatever type of object we have, the data field of that can be turned into a string with its own toString method, which, you know, integers have a toString, strings have a toString, rectangles have a toString. So changing this to work with a different type of object for its data is mostly just syntax, right? It's mostly just saying I have to use the word integer here or the word rectangle, right? And that's why generics are a thing in Java, because you're really just kind of doing a macro substitution. And here, when you write a generic, and we'll do that later, what you would do is say, put in the type of object, right, that E identifier you see in the documentation, plug that in here. So if you construct a MyList with type rectangle, this would be replaced with RECT, right? So that's where generics kick in. Is that a question, or? All right, I hear microphone noise. Is that a question or background? That might be background noise. All right, let's just print out listy as a string. Right, well that's not very exciting. It's that default toString method we get from objects that just show me the name of the object, the name of the class, and then a internal reference. So let's write a toString method. And we've almost got it. We've almost got it with our print method. So public string toString. So we'll start off with an empty return string, which I'll just set to quote quote. We'll make our temporary node equal to first node, and then while that's not null, instead of printing, what we're going to do is just concatenate right? Or let me do it like this. Let's put the word inside quotes. So I'm escaping my quote so it doesn't end my string. So this is just a single double quote. So I'll tack that on to my return string. And let's initialize return string to a parenthesis. And we'll build up our return string. We'll move down to the next node, and when we're done, we'll throw a closing parenthesis on the end just to make it look a little neater. And then we'll return that string. So by writing that one method, now when we concatenate listy to a string, we get this comma-less list of words. I thought that strings were immutable, so each time you concatenate, you are just creating a new object of type string, right? Would it be better to use string builder or string buffer in this case? Yeah, so when you do this kind of thing, when you say string equals, yeah, you're building a new string. That's okay. Yeah, it's potentially an efficiency thing. I'm not sure that string builder will be more efficient though. So yeah, this is fine to use. Generally not a problem. All right, so so that's, you know, linked list example. So hopefully that makes some sense. And we're dealing with edge cases, right? If we did a Sentinel node, we'd skip most of those edge cases. But it's good to know how to deal with them and not be scared off by them. Will we ever be extending classes in Java, like extending the linked list class? Yes, absolutely. We will talk about class extensions in a few weeks. And the idea there is that basically if you want to make, let's say we have this linked list class, okay, that, you know, it's got an add method, it's got a print method, it's got a toString method. Suppose we also wanted to add something else, right? Like something that would turn your linked list into an array, okay? Rather than write an entirely new linked list class, right? Or taking the code from that linked list class and using it to make an entirely new class, we can say, let's create a super list which extends MyList. And we kind of inherit all of the methods and fields from that base class, the MyList, and we get a new class that starts with all of that stuff, and we can add things to it, and we can change things. If we wanted to change what the toString method did, we could write our own version of toString in that extended class, and it would look exactly like the base class, but it would have our own version of toString. And class extension is one of the keys to object-oriented design. So we've talked about this briefly before. When we have a linked list, Java utility linked list, it's actually an extension of an abstract sequential list, which is an extension of an abstract list, which is an extension of an abstract collection, which is an extension of an object, right? And so this class has a number of methods available to it, right? But it also has methods that it inherited from these other classes, such as the iterator from the abstract sequential list, and the equals method from the abstract list, and at the base, we always inherit things from the object class. So yeah, class extension is definitely something that we'll talk about. And it's another one of the really fun parts of object-oriented programming, because you get to start with something that's already there and just build on top of it, and that's really cool. All right, well, where do we go from lists? We always go to trees. So let's think about a class called tree. And it's going to be a binary search tree. It's going to work a lot like the 222 trees. And we're going to stick with recursion, right? So we won't do a lot of looping. We'll do our inserts and traversals and so on recursively. And there's one little detail we need to work with. So our tree is going to be composed of nodes, right? And our node structure is going to look something like this. There's going to be a node to the left. There's going to be, let's go back to integers, so an integer data and a node to the right. And when we recurse, we're going to do things like say, if there is something to the left, then traverse the thing to the left. And then print the data, and then if there's something to the right, traverse the thing to the right. Or if we're inserting, we're going to say, if the thing we're inserting is less than this node's data, insert it into the left subtree, and then set left equal to the result of that. When we do those operations, we're inherently doing them on nodes, okay? But a main program that's interacting with this is going to want to interact with trees. So our main program is going to do something like this. Tree t equals new tree, and then t.add, and then t.print, and so on. So the tree class is going to really be a wrapper around a bunch of methods that are actually going to be part of the node class. Okay, and this is a little strange, but once we actually write this, it will hopefully make good sense. But the actual recursive code for inserting, traversing, searching, all of that stuff, those are going to be things in the node class. Okay. And the tree class is really just going to be a handle to the root of the tree and then some wrappers around the methods in the node class. Because the main thing the tree does for us is it stores the root. Now, if the user wanted to deal with, being responsible for the root, you could do that and you could just work with a node class, but your code would look something like this, right? Node root equals null, maybe. And then when I want to insert something, I have to know that it's empty, and so I do root equals new node, right? And then I can do root dot add and add some more stuff, and I can do root dot print, and so on and so forth, right? But this part's a little awkward, right? The user has to know if the tree exists or not, and if it doesn't, you have to call the node constructor to make the first root node, and that's just kind of, it sort of breaks the symmetry of it, as opposed to this that we really want, where we just say, give me a tree, add some stuff, delete some stuff, print, search, etc. So tree is going to be a wrapper basically around these things like root.add, root.print. So we'll start specking out some code for that tomorrow, and I'm leaning towards PA3 being related to binary trees, working with decision trees, so a different type from a binary search tree, but still a binary tree. So we'll probably end up for PA3 actually wiring trees together by hand. Okay, so we'll go through examples of this tomorrow. And I will leave it there. I'll let you out 60 seconds early. All right, have a good day. I will catch you next time.